Hi everyone, today we're going to be looking at what resistivity is in materials, also be able to use the equation and how we derive this equation, techniques and procedures to determine the resistivity. So that's pack 3, is a required practical that we need to do. How the resistivity of metals and semiconductors vary with temperature, and what we mean by negative temperature coefficient for a thermistor, and the light-dependent resistor as well, how it varies with light intensity. Okay, so what is resistivity? Well, as you can see in the picture here, you have different items, different metals or semiconductors and insulators. They all have different shapes, different cross-sectional areas, and so on. Now, we already know that the length affects resistance. We know that the cross-sectional area affects resistance, and the material itself affects it. So when we talk about resistivity, we talk about specifically how material itself opposes electron flow. So resistance is for a specific component, whereas resistivity is an electrical property of a material. So in other words, resistivity doesn't get affected by any changes in the dimensions of the material. It's a fixed value for that material, and we call it like that it's an intrinsic property of it. So if I change the length and cross-sectional area of copper, for example, here, resistivity will never change. It's a specific property of copper, but the resistance will change. So resistivity doesn't get affected by physical properties, resistance does. And resistivity is a property of the actual material. However, we will see that resistivity is different for the same material at different temperatures. So we'll come across that in a second, but just remember that doesn't get affected by physical things, only gets changed by temperature. And that's because resistance of that material changes at a specific temperature. We'll come across it in a second. Okay, so let's go through what resistivity is in terms of the calculation, in terms of the equation. So we represent resistivity using the Greek symbol rho. It's a Greek letter. And we calculate it using this equation here. So resistivity is equal to resistance times cross-sectional area divided by the length. So in terms of symbols, rho is resistivity, resistance is R, which is always measured in ohms, cross-sectional area, which is in meters squared, and we divide it by the length, which is in meters. So what we have is that resistivity, since we have ohms meters squared divided by meters, it will be ohm meters. So the resistivity of a particular material does vary with temperature, and that's usually due to the fact, so the quote resistivities at different temperatures for a specific material, because it does rely on resistance, as you can see from the equation that resistivity is directly proportional to R. But before I move on, I want you to understand this equation a little bit more, so I'll use this space above to write. Now, for a given current passing through a component or a wire, if I increase the length of the wire, the potential difference increases across the wire, which means since V is IR, for a fixed current, so if that was fixed, then the resistance increases as the potential difference increases. That means that resistance is directly proportional to length. Then we have the resistance and cross-sectional area. Now, if I increase the cross-sectional area of a wire, the opposite happens. The resistance will drop. And that's because for any potential difference, if I double the cross-sectional area, I will double the current going through it. So in this case, the resistance is inversely proportional to the area. As if I double, so if I, for a given potential difference for a fixed PD, if I double the area, then the current will increase, so that will be fixed number, which means the resistance will drop by half if I double current. So resistance is inversely proportional to cross-sectional area. And if I combine the two expressions, I come with resistance is directly proportional to the length over the cross-sectional area of the wire. And since we know that resistance, there's a direct proportionality between these values, then that means that it's K over L over A. Now that K, our constant, is the resistivity. So R is equal to rho L over A. And if I rearrange, rho is RA over L. Okay, so to define resistivity, we just simply use the equation again. So resistivity at a given temperature is the product of resistance and its cross-sectional area divided by length. So we know already that for any material, if the temperature increases, the resistance, well, for most conductors actually, the resistance increases. And since we know that resistivity is directly proportional to resistance, so does resistivity increases if the temperature increases. Now there are, we know that there's conductors, semiconductors, and insulators. They have very different values for resistivity. So good conductors have a resistivity of this order. Insulators have a resistivity of this order. And semiconductors is something in between these two values. So there is an extreme of values in terms of resistivities. And you can see that conductors, since they have a very small value of resistivity, those type of materials resist the electron flow less than insulators will. Okay, so let's look at a couple of examples. You're told that you have a cylindrical wire of length this much. So the length, we need it in meters. That would be 1.35 meters. Has an average diameter. So it gives us the diameter, we like radius, times 10 to the minus 3 because it's in millimeters. We told the current, I, which flows through the wire when there's a potential difference. We given potential difference and to calculate the resistivity to two significant figures. So I underlined and labeled my values. You can make a list of them if it helps you. We know that resistivity can be calculated using RA over length. We also know that resistance is V over I. So if I substitute that in, it will be resistivity is VAIL. And I just simply have to place my values. But for the cross-sectional areas, it's a cylindrical wire. It will be the cross-sectional area of a circle, which is pi r squared. So pi r squared over IL. And I'm just going to simply place my values in, which is 16 times pi times 0.4 times 10 to the minus 3 squared, divided by the current, which is 2.4 times the length, 1.35. So it comes out to be 2.48 times 10 to the minus 6 ohm meters, but it wants it to significant figures, so that's 2.5 times 10 to the minus 6 ohm meters. You can notice from here that the value is quite logical. At the end of the day, it is a wire, which is all of the wires are made up of conducting materials, so the value does seem logical. It's quite similar question here, but in this case, we're asking to calculate something else. So it gives us the resistivity of a wire. It's telling us to calculate the resistance when the length is 0.8 meters, and this is the radius. So once again, wire is pi r squared. So I will rearrange for r. So we know this equation. I will rearrange for r to be the subject because that's what I need to calculate. So I'll multiply both sides by L and divide both sides by A. So just simply place the numbers in once again. Times 0.8 divided by pi r squared, which is times 10 to the minus 4 squared. Yeah, just put that in the calculator and you get the answer. So the next part I wanted to talk about is the practical work. How can I have a plan to investigate the resistivity of a wire? What measurements will I need to make? What safety precautions? And how can I use my results to get the resistivity? So these are the things I'm going to go through now. They're very important. It's one of the very important experiments. It usually gets tested in exams. So let's start with how can I investigate resistivity? So if this is my equation for resistivity, that means I need to be able to make several measurements, and obviously not just one set of measurements, because I need to get average to make my experiment more accurate and precise. So I have to be able to measure resistance. We can do that using an ammeter and voltmeter. I also need to be able to measure the cross-sectional area of a specific wire, which will be fixed, and the length of a wire, which I will be changing in order to be able to get different values for R, for resistance. The cross-sectional area will be constant because I will be using the same wire, and that way I'll be able to use these values to get resistivity. So a very good setup would be to connect. By the way, this is not the exact way that you were supposed to connect it, but I will get to it when we do the experiment. So I will connect a wire of a specific length, and I will keep changing that length using crocodile clips. I will need a voltmeter parallel to it, an ammeter in series with it, and basically as I change the length using the crocodile clips of the wire, I will be able to measure resistance at different lengths. Now for the length, I can use a meter ruler. So here I use ammeter and voltmeter, meter ruler. But for the cross-sectional area, you will need to use a micrometer because our rulers cannot measure the diameter of a tiny wire. So what we do need to do is use a micrometer. I will show how to use that in class, but it makes measurements that are very, very small, so it can measure to millimeter. Obviously, once we get our diameter, we have to divide it by 2. And to use a micrometer, you need to take the reading at 3 different places. So let's say at 3 different parts of the length, and you need to average that. So by take measurement at 3 different spots of the wire and average. Because wires are not always fully 100% perfect, you might need to do that in order to make sure that you take the average of the thickness or diameter of the wire. So yeah, we'll take these measurements. We will be changing the length, so length will be changed and resistance will be measured. The cross-sectional area will be our control variable. So just to remind you, what we are changing is called the independent variable, and what we're measuring is the dependent, and then the control variable is the cross-sectional area. Also, we need to make sure that the temperature of the wire doesn't change, because that will affect the resistance and hence the resistivity, and we don't want that, because there's going to be another factor besides changing the length that will affect resistivity. So what we would like to do is make sure that we use a switch and open up the switch in between readings so the wire doesn't heat up. So and also use a very low current. So low current, so it doesn't heat up the wire too much, and open the circuit between readings to avoid any heating up of the wire. Now, safety precautions are usually to not touch the wire because it might get too hot. Don't place it near water sources and so on. Now, how can we use our results? So what we will end up having is a length against, V, I, and then using V and I, we can calculate resistance. But we can plot a graph of this. So we can plot the resistance against the length. And if you look at the equation and compare it and rearrange it, actually, let's rearrange it for R. That's rho L over A. So as you can see, Y is equal to mx plus c can be used to, so the equation of a straight line can be used to be related to this equation. This is a very important part. We'll be using it for a lot of different graphs in physics. So please get that right. If you don't understand it, let me know in class. So my y-axis is R. My x-axis is L. So this is the x-axis. I don't have a plus something component, so there is no y-intercept, which means the line goes through the origin. This is a straight line. It will look like this. And that leaves me with the gradient, which should be the resistivity divided by the cross-sectional area. So if I use the biggest triangle, which you need to use, by the way, in the exams, and if you don't show this, you don't get the marks. If you show a little triangle, you won't get many marks at all either. You need to use most of your values. So if you get the gradient, your gradient will be equal to rho over A. So if you want to get the resistivity, you simply multiply the cross-sectional area by the gradient of your line, and that's how you get your resistivity. Okay, so now I'm going to go back to the content that we need to know and go through what we spoke about so far. So we talked about the resistivity and how to measure the resistivity of metal through an experiment. Now we're going to look at the variation of resistivities for metals and semiconductors as well with temperature. But before I go to that, I wanted to mention something very quickly. So I mentioned before that resistivity varies with temperature, just like resistance does. Usually we quote a resistivity at a specific temperature. And usually that temperature is room temperature. You don't need to know this equation. But you should be able, if this equation is given to you as part of an experiment, you should be able to rearrange or even figure out how to do the practical. So just a quick mention of it. This is the specific resistivity at a specific temperature that you're trying to achieve. And this is the resistivity at a quoted temperature, usually room temperature, so where you will start taking values. You find this in a data booklet or an online website that has data that have been measured already. Alpha is a temperature coefficient, which is also quoted in the formula in the data booklets. So these are constants, this and this, that should be given or investigated before an experiment. This is the temperature that the material will need to reach, and this is the temperature at which the resistivity is quoted. So if it was a room temperature, then I'll need to use that temperature. So I mentioned that bit. We move on from here. So the variation of resistivity of semiconductors and metals with temperature. We already mentioned this, but I will talk about it again. Now, conducting material, we said, if the temperature of the metal increases, so does the resistance increases, and since resistance is directly proportional to resistivity, resistivity will also increase. But when it comes to semiconducting materials, like a thermistor or an LDR, now thermistors are actually made from semiconducting materials, and we say that they have a negative temperature coefficient, meaning that the resistance will drop as temperature increases. So this is the opposite of what happens from conducting materials. So as temperature increases, the number density, so that temperature increase allows more free electrons to be released. So that means that the number density increases, which means more current, which means a lower resistance as the temperature increases, basically, and more current will flow. That's because the atoms in semiconducting material can gain enough energy to release more electrons with thermal energy. So the more thermal energy they get, the more electrons they will release. So thermistors are usually used in sensing circuits, so in the ovens, in a baby incubator thing. I don't know if that's the correct word, but when babies are born prematurely, they place them in this machine that has to be regulated. And we did speak in the previous lesson about the experiment that you could do to figure out how resistance changes with temperature. We said that you need an ammeter, you need a voltmeter to measure the resistance, you need a thermometer, which is not shown here, to measure the temperature. So you should record the voltage and current, so potential difference in current at equal time intervals, let's say every 5 degrees temperature change. So instead of using a Bunsen burner, you could use a water bath, which is less dangerous than heat. You could use, instead of a voltmeter and an ammeter, an ohmmeter, and you need to ensure that you're always mixing the water in order for the temperature to be uniform everywhere. So thermistors are usually used depending on what job you need to get them done for. So they will have different resistance range. And as you can see from the graph, there's a very sharp drop between certain points compared to other resistances. So depending on what we want to use them for, they need to be described in that way. And the last thing we will talk about in this lesson is the LDRs. Now, they behave very similar to thermistors. So the more light intensity that's incident on them, the lower the resistance. That's because LDRs, as you shine more light is a form of energy as well, right? So when we see light, it's a transfer of energy, it's a wave. So the more light, the more energy atoms will get in the semiconducting material of the LDR. So the more energy they get, the more electrons they will release. Which means the number density increases, which means the current increases, which means the resistance decreases. So for an LDR, we will have exactly the same graph as for resistance against light intensity, though, not temperature, which will go from a specific resistance at 0 light intensity, and it will drop exponentially as we increase the light intensity. This is the explanation of why this happens. So in dark conditions, we will have a low number density. So whereas dark conditions, so there will be higher resistance, and as we increase the light intensity, the more energy the atoms get, the more electrons they release. The higher the number density, the lower the resistance. So you do need to remember the graphs, you need to be able to sketch them. They're the same for LDRs and thermistors, however, the only thing that changes is for LDRs is the light intensity, for thermistors is the temperature. You should also be able to describe a simple experiment to get the resistance and in terms of light intensity, which is quite similar to thermistor, but instead of using water to heat it up, you will use a light bulb and then move. So if you have, let's say this is my light bulb, and this is my LDR. Oh, sorry. That's my LDR. Then I will have to move the LDR closer at a specific distance to change the light intensity. So obviously, the closer you get to the light bulb, the higher the light intensity. You should have a sensor that measures the light intensity only. That's the only difference. So you need a sensor, a light sensor, and a voltmeter and ammeter, and that's how you will get the resistance against light intensity. So this is it for this lesson. Just go back quickly to the learning objectives. So we talked about the light-dependent resistor in terms of light intensity and how we can use that. And we also spoke about the negative temperature coefficient of the thermistor as it varies with temperature. And we also looked at how resistivity varies in metals and semiconductors with temperature. If you have any questions, please write them down. We'll go through it in the lesson.